Hello everyone. Welcome back to the FT Share channel. In this ever-evolving automotive world, Porsche, known for its innovative and high-performance vehicles, is now designing a revolutionary six-stroke engine. This engine is a unique combination of the high performance and simplicity of a two-stroke engine with the efficiency and eco-friendliness of a four-stroke engine. With this six-stroke engine development, Porsche aims to create a more efficient, environmentally friendly engine while maintaining the outstanding performance we always expect from Porsche cars. However, a big question arises. Why is Porsche still ambitious about patenting its six-stroke engine, despite the planned ban on selling combustion engine vehicles in 2035 and the global trend towards vehicle electrification? So, in this video, we will thoroughly explore the differences between these engines, how the six-stroke engine works, its advantages and disadvantages, and finally, Porsche's reasons for developing this innovation and its potential for mass production. Porsche's six-stroke engine is not the first six-stroke engine to exist. As we discussed before, there are other six-stroke engines that can even operate with a combination of water and fossil fuels. While Porsche's six-stroke engine has only recently gained attention, this engine has actually been in development for quite some time, dating back to the early 2000s. The primary goal of this development, as we mentioned earlier, is to address the weaknesses of two-stroke and four-stroke engines, especially regarding emissions and fuel efficiency, while maintaining high performance. After nearly 5 years of development, Porsche officially patented this technology in 2006, by combining two combustion cycles. By 2010, Porsche began testing the six-stroke engine in prototype vehicles to evaluate its capabilities in real-world conditions. However, the mass implementation of six-stroke engines remains limited, as the focus has largely shifted to developing electric and hybrid vehicles. Before diving deeper into the details of how Porsche's six-stroke engine works, we'll first briefly review the mechanisms of two-stroke and four-stroke engines for better understanding. If you're already familiar with how two-stroke and four-stroke engines work, you can skip ahead to this timestamp. As we know, a two-stroke engine operates with a simpler mechanism compared to a four-stroke engine. It only requires one complete crankshaft revolution to complete one combustion cycle. Step 1. Intake and compression stroke. As the piston moves upward, the air-fuel mixture in the combustion chamber is compressed. Simultaneously, a new air-fuel mixture enters the crankcase. Step 2. Power and exhaust stroke. When the piston reaches the top dead center, the spark plug ignites the compressed mixture, causing combustion that generates power. The combustion forces the piston downward to the bottom dead center. At the same time, the new air-fuel mixture from the crankcase enters the combustion chamber through the intake port, while the exhaust gases exit through the exhaust port. This process repeats continuously, and that's how a two-stroke engine works. The advantages of a two-stroke engine include simplicity, lighter weight, and the ability to produce more power since it only requires one crankshaft revolution per combustion cycle. However, its disadvantages are notable. Two-stroke engines are less efficient in combustion as the exhaust gases and the new mixture often mix, leading to higher emissions and greater fuel consumption compared to four-stroke engines. So, while two-stroke engines are simpler and lighter, their efficiency is lower than four-stroke engines due to less distinct separation of combustion and exhaust processes. Now, what about four-stroke engines? A four-stroke engine operates through four main steps across two crankshaft revolutions: intake, compression, combustion, and exhaust. Step 1. Intake stroke. During the intake stroke, the piston moves from TDC down to BDC. As the piston descends, the intake valve opens, allowing the air-fuel mixture to enter the combustion chamber. At this point, the combustion chamber is fully filled with the air-fuel mixture. Second, compression stroke. After the intake valve closes, the piston moves back upward. During this upward motion, the air-fuel mixture in the combustion chamber becomes compressed, making it denser and hotter. This compression process is crucial because the denser the mixture, the more efficient the combustion will be. Third, power stroke. Next is the combustion process. When the piston nears TDC, the spark plug ignites the compressed air-fuel mixture. This combustion generates high pressure, forcing the piston to move downward with great force. The energy produced from combustion drives the piston down, spinning the crankshaft and ultimately propelling the vehicle. Lastly, exhaust stroke. The final process is exhaust. After the piston moves downward, the exhaust valve opens. At this point, the piston then moves back up to expel the combustion gases into the exhaust system. After this, the engine is ready to begin the next cycle. As we've explained earlier, a four-stroke engine requires 2 full revolutions of the crankshaft to complete one combustion cycle that generates power. This makes the four-stroke engine more efficient and produces fewer emissions than the two-stroke engine, although it is slightly more complex and requires more components. So that's how the two-stroke and four-stroke engines work, along with their advantages and disadvantages. Now, what about the main highlight of our discussion, Porsche's 6-stroke engine? As we can see here, this engine uses an eccentric gear on the planetary gear system to create 2 top dead centers and 2 bottom dead centers. In its anatomy, the main difference between the 6-stroke engine and other engines lies at the bottom of the engine, which employs a gear system. The first components we encounter are the ring gear and the planetary gear. When we look more closely at the planetary gear section, we can observe elements that are offset by the planetary gear mechanism. The core of this system is designed eccentrically, allowing for more complex and precise movements. The eccentric mechanism is key to generating the hypocycloidal path that supports the performance of the 6-stroke engine. The hypocycloidal path is a critical concept in the design of Porsche's 6-stroke engine mechanism. This path refers to the motion trajectory produced by the eccentric gear system. In this mechanism, a point on a smaller gear moves along the inner side of a larger gear, creating a unique hypocycloidal trajectory. When additional components like the connecting rod and piston are added, the motion produces 2 top dead centers and 2 bottom dead centers. Looking at the engine, the first TDC is where the piston is at its highest point within the cylinder, and on the hypocycloidal path, the point is here. For the second TDC, the piston is slightly lower than the first TDC, and on the hypocycloidal path, the point is over here. For the first BDC, not far from the second TDC, the piston is slightly higher than the second BDC, and on the hypocycloidal path, the point is here. Finally, the second BDC is where the piston is at its lowest point within the cylinder, and on the hypocycloidal path, the point is located here. In Porsche's 6-stroke engine, the eccentric gear system transforms the piston's linear motion into efficient rotational motion. This design also enables 2 combustion processes in one working cycle, regulated through the hypocycloidal motion pattern. The advantages of this mechanism lie in its capabilities, such as precisely controlling 2 top dead centers and 2 bottom dead centers, reducing engine size without sacrificing performance, enhancing combustion efficiency by utilizing dual combustion in a single cycle. Additionally, the eccentric gear mechanism allows for more complex piston motion, supporting high efficiency and performance in line with Porsche's characteristic innovations. Unlike the epicycloidal path, which is generated by a point on a larger gear as it rotates around a smaller gear, the hypocycloidal path is the opposite. It is generated by a point on a smaller gear as it rotates inside a larger gear circle. The hypocycloidal pattern is more compact and is often utilized in engine mechanisms. In addition to the ring gear and planetary gear, another difference in the 6-stroke engine is the scavenging port located between the first and second BDCs. This port allows fresh air and fuel to enter the cylinder when the piston is at the second BDC. The distance between the two dead centers is designed to match the port height, aligning with the eccentric gear displacement. The intake port, located at the bottom of the cylinder, only opens after the piston passes the first BDC. This design ensures efficient air and fuel supply into the combustion chamber. In addition to the port at the bottom, the engine also has intake and exhaust valves at the top, similar to conventional engine designs. This combination of ports and valves allows the six-stroke engine to operate optimally, improving airflow and combustion efficiency. Now, how does it work? First step, intake. Starting from the second TDC, the intake valve opens, allowing air and fuel to enter the cylinder as the piston moves downward. This step ends at the first BDC, where the eccentric element ensures the piston keeps the lower port closed. Second step, first compression. The piston moves upward, compressing the air-fuel mixture. Before reaching the first TDC, the mixture is ignited by a spark, ending the first compression step. Third step, first combustion. After ignition, the combustion pressure pushes the piston downward, generating torque. As the piston reaches the second BDC, the lower port opens momentarily, allowing fresh air-fuel mixture to enter, while the exhaust valve at the top also opens to expel combustion gases. Fourth step, second compression. From the second BDC, the fresh air-fuel mixture, mixed with residual exhaust gases, is compressed as the piston moves upward to the first TDC, where it is ignited again. Fifth step, second combustion. This combustion generates additional torque, though smaller than the first due to residual gases. The piston moves downward to the first BDC, where the crankshaft eccentric gear halts the step. Sixth step, exhaust. The piston rises again, expelling residual gases through the exhaust valve at the top. This step concludes as the piston reaches the second TDC, completing one full cycle and initiating a new cycle. And that is how the Porsche six-stroke engine cycle works. Now, what are its advantages? The first advantage of the six-stroke engine is its simplicity and use of conventional technology. The six-stroke engine uses components commonly found in the automotive industry, such as gears, crankshafts, connecting rods, pistons, and small ports at the bottom of the cylinder. This design leverages proven technologies, making it easier to implement without requiring radical innovations. Second, the single-stream scavenging system. This machine employs a scavenging system commonly found in two-stroke diesel engines, such as those used in ships, trains, and various industrial machinery. The system is designed to maximize airflow efficiency through a combination of scavenging ports and conventional valves. The scavenging ports, located on one side of the cylinder, introduce fresh air into the combustion chamber. Meanwhile, the conventional valves on the opposite side ensure the exhaust gases are effectively expelled. This design leverages a proven concept to enhance engine performance across various industrial applications. Third, minimal camshaft modifications. The modifications to the camshaft in this engine are relatively simple. In a four-stroke engine, the camshaft rotates at half the speed of the crankshaft. However, for a six-stroke engine, the rotation speed is adjusted to 1/3. This adjustment is achieved by slightly increasing the size of the camshaft gear, maintaining the correct speed ratio between the crankshaft and the camshaft. Additionally, one extra lobe is added to the exhaust cam to ensure the exhaust valve opens precisely according to the engine's working cycle. Fourth, low development costs. Since the technology used is already widespread and the required modifications are relatively minor, the six-stroke engine does not demand significant investment in research and development. This makes it more cost-effective to produce compared to engines featuring newer, more complex technologies. Finally, the fifth advantage is higher air pressure and lower emissions. When the engine operates under high boost pressure, such as 3 bar or 45 psi, the air-fuel mixture needs to be enriched to prevent engine knocking. However, using a rich mixture has a downside in that not all of the fuel combusts completely. As a result, the exhaust gas contains unburned fuel, which can increase pollution if released directly into the atmosphere. The six-stroke engine offers an innovative solution to this issue. Instead of expelling exhaust gases directly, most of the exhaust gas remains in the cylinder, while only a small portion exits through the lower port. The retained exhaust gas is recompressed and reignited, allowing any remaining fuel to combust fully during the second combustion cycle. This process produces much cleaner emissions, making the engine more environmentally friendly and capable of meeting stringent government emission standards. With these advantages, the six-stroke engine not only harnesses high boost to deliver substantial power, but also ensures environmental sustainability. This makes it an ideal solution for modern vehicles that demand high performance without compromising eco-friendliness. Although the six-stroke engine design holds significant potential, there are some drawbacks and technical challenges that must be addressed. These challenges primarily concern the use of gears, piston design, engine balance, and vibrations. With proper adjustments and innovations, these weaknesses might be mitigated. The first disadvantage is the energy loss due to gear use. One significant drawback is the energy loss caused by the addition of extra gears in the eccentric mechanism. These added gears can increase mechanical losses, negatively affecting the engine's energy efficiency. Furthermore, the additional components complicate maintenance processes and raise the risk of mechanical failure over time. The second disadvantage is the long piston design. To meet design requirements, the piston must be sufficiently long to close the scavenging port at the bottom of the cylinder when at the first top dead center. However, this long piston design has several consequences. For instance, the heavier piston adds to the reciprocating mass, which increases vibrations during engine operation. These vibrations limit the engine's maximum rotational speed, effectively capping its RPM. As a potential solution, the scavenging port mechanism could be replaced with additional valves. This approach would allow for shorter piston designs, reducing weight and vibrations while enabling the engine to operate at higher RPMs without compromising performance. The third disadvantage is non-ideal engine balance. The piston strokes in this engine are asymmetrical, leading to imbalances in both primary and secondary forces. These imbalances create minor vibrations during engine operation. Although these vibrations are not overly significant, they still need to be addressed to ensure user comfort and maintain overall engine performance. Lastly, there is the issue of vibrations from planetary gears and eccentric elements. Planetary gears rotate at high speeds, generating centrifugal forces that add to the engine's vibrations. Additionally, eccentric elements contribute lateral forces due to their asymmetric motion, creating extra vibrations. Even small misalignments in the connecting rods can exacerbate this issue, further increasing the overall vibration of the engine. Now, let's discuss the solutions to minimize vibrations. Optimizing the cylinder configuration is crucial for reducing vibrations. Porsche suggests that six-stroke engines perform best with cylinder configurations in multiples of 3, such as 3, 6, 9, or 12 cylinders. A six-cylinder engine is considered ideal, as many Porsche vehicles use this configuration, which is easier to balance and compatible with six-stroke engine designs. Additionally, anti-vibration devices such as balancer shafts or vibration-damping materials can be employed to minimize vibrations to nearly imperceptible levels, thereby improving comfort and engine efficiency. Now, the question arises, is a six-stroke engine more powerful than a four-stroke engine? In principle, the six-stroke engine has an advantage in the number of combustions per rotational cycle compared to the four-stroke engine. In one full rotation, which is 720 degrees, both the six-stroke and the four-stroke engines produce one combustion event. However, the advantage of the six-stroke engine becomes apparent after the first 720 degrees. It immediately proceeds with a second combustion, while the four-stroke engine requires another 360 degrees to complete its next combustion, totaling 1080 degrees for the second event. So, if we compare over a full 7200-degree rotation, the four-stroke engine produces 10 combustion events, while the six-stroke engine produces 13.34 combustion events. This indicates that the six-stroke engine has the potential to generate up to 33.4% more power than the four-stroke engine. However, it should be noted that the second combustion in the six-stroke engine is not as strong as the first, as there are still residual exhaust gases in the combustion chamber. Taking this factor into account, the realistic power increase is around 25%. Porsche continues to develop the six-stroke engine, even though the European Union plans to ban the sale of ICE vehicles starting in 2035. This move is backed by several strategic reasons that highlight the engine's potential for the future. Let's start with the European Union's agreement on e-fuels. On March 25, 2023, the EU reached an agreement with Germany, allowing ICE vehicles to continue being sold after 2035, as long as they use e-fuels. Now, what exactly are e-fuels? They're synthetic, eco-friendly, carbon-neutral fuels. Although they're still expensive and hard to produce at the moment, the expectation is that this technology will become more affordable and widespread before 2035. And Porsche, being part of the Volkswagen Group, has already invested heavily in e-fuel development to ensure the long-term sustainability of internal combustion engines. Now, moving on to the advantages of the six-stroke engine. The first major benefit is its high efficiency and performance. The six-stroke engine offers better fuel efficiency and more torque compared to the traditional four-stroke engine. With this technology, Porsche can boost vehicle performance without compromising on emissions. Next, let's talk about how environmentally friendly this engine is. Thanks to its recombustion process of exhaust gases, the six-stroke engine produces significantly lower emissions. Additionally, it's perfectly compatible with e-fuel, which aligns with future emission standards, particularly those set for 2035. One of the key aspects of this engine is its use of conventional technology. The design of the six-stroke engine incorporates many components already familiar within the industry, such as eccentric gears and scavenging ports. This makes it easier to transition into production without major overhauls to existing manufacturing facilities. Porsche is protecting its innovation by patenting the six-stroke engine design. This ensures that they remain leaders in internal combustion engine technology and gives them the flexibility to license or market this technology to other manufacturers in the future. Looking to the future, Porsche sees great potential in e-fuel. The six-stroke engine can leverage this synthetic fuel to deliver high performance while meeting emission standards. If e-fuels become more affordable and widely available, internal combustion engines could remain relevant even after 2035, especially in high-performance vehicle segments like Porsche. Finally, Porsche's commitment to high-performance vehicles is evident. As we all know, Porsche has a long history of creating cars that prioritize engine performance. With the six-stroke engine, they can continue this legacy while meeting the environmental regulatory challenges ahead. In conclusion, the six-stroke engine is part of Porsche's long-term strategy to stay relevant in an automotive industry that's transitioning towards sustainability. By using e-fuels and innovative combustion technology, Porsche sees a huge opportunity to create eco-friendly ICE vehicles that still meet future emission standards. And when compared to other six-stroke engines, this one, backed by substantial investment in development, has even more potential for future application. So, what do you all think about Porsche's six-stroke engine? Don't hesitate to share your thoughts in the comments below. And, as always, If you have any corrections or additions to what we've discussed, feel free to drop them in the comments as well. Thanks for watching, and I'll see you in the next video.